perhaps what we started to see evidence for. And this would be a very interesting theory because if there were some system in the real world described by this CFT, you wouldn't have to tune any parameters in your experimental system in order to reach the critical point. Okay? The number of relevant operators corresponds to how many parameters you have to tune, right? So if there are no relevant scalars, then you don't have to tune any parameters. So this would be very interesting because it would be an example of what people sometimes call self-organized criticality.
They should have seen this lab.
Does it mean they should have seen it? Who's they? Well, it depends on whether there's whether it's experimentally. I mean, it depends on whether there's some real-world system that realizes it. So actually, there are experimental systems that people have been getting very excited about recently, containing Majorana fermions. So there's been a lot of excitement in the condensed matter community about realizing Majorana fermions as modes propping on the boundaries of topological materials, topological superconductors, and topological insulators. So if there were a system that realized it, it might be some boundary theory proving a lot of topological material. And I think people are really just starting to explore the properties of this. So maybe we can still do something.
But then, I mean, typically these edge modes, theories of edge modes don't have stress tensor. So it would be a good thing to see whether this theory does have stress. I mean, maybe you have to tell us that it does.
Good. I think there are definitely some cases where the edge theories do have stress tensors. So that's but yeah. So I should say, so that's a good question. We can ask if this theory has a stress tensor or not. And I don't know the answer to that yet because these are fairly recent studies and we haven't probed that question. We've computed bounds on the central charge, and they don't show any obvious features at this point. So I think we're going to have to put in some more information what we have. So I think this is a good place to stop. I'm out of time, but I hope I've convinced you that the Bootstrap is very exciting, and we can make contact with many node systems, but we can also potentially use it as some discovery tool for finding new CFTs that people didn't know about. So thanks a lot.
Other questions or comments?
Can you say quickly some progress in the higher linear memory, 5 or 16?
Yeah. So good. So there's a group of people that did the Bootstrap for 62,0 series, and so this is Leonardo Rastelli, Crispy, and these collaborators, and they've managed to so you can set up the Bootstrap for 4-point functions of the multiplet containing the stress energy tensor. This is a case where the super conformal blocks are known. So this is a bottleneck for doing many Bootstrap studies in super conformal theory. You have to know the super conformal blocks structure. But that's a case where we do know it. And that's also a case where there's this interesting story where there's a certain class of operators in the theory whose correlation functions are described by 2D chiral algebras. So you can do there's a twisting you can do to map, say, the 3-point functions of certain protected operators to a 2D chiral algebra. And so you can solve that 2D chiral algebra exactly, and then use that as input into the Bootstrap problem for unprotected operators. Then you can get bounds including unprotected scaling dimensions. You can look at constraints on the central charge and so on. And they really started to see, they we've seen some evidence that there's a minimal central charge, and the minimal value of that central charge seems to be converging to the central charge of the simplest 2, 0 theory, the A1 theory. So there's a lot of progress there. Some people have also done the Bootstrap in 5D. So there's a question in 5D of whether, say, the ON vector models exist in 5 dimensions. I guess you can construct perturbative fixed points in 6 minus epsilon dimensions and then try to extrapolate epsilon to 1. But there's a question. There's some question about whether this theory really makes sense because it looks like the vacuum may be unstable because the 6 minus epsilon dimensional description has cubic scalar interactions. But there was a group of people at Princeton that tried to do the bootstrap for this theory, and they actually found some kinks, which seem to match onto the large n perturbative calculations of the 5D Owen models. And at smaller values of n, these kinks sort of wash out and go away. And I think it's an open, the right interpretation right now is an open question. So they tried to interpret it as indicating that maybe there's some bottom of the conformal window, but you could also interpret it as, say, there's some problem with unitarity in this theory that's very suppressed and large n, but it becomes more and more important for the small n theories. So there's an interesting story there.
Yeah, so how much do you know about the RG flows between different things using, so for example, you can parameterize some of the relevant operators in this theory.
Yes.
So now suppose I take my CFT and I switch on a relevant operator deformation. Can you say anything about like where the thing flows? Or...
Oh, well, that's in general that's very hard. I mean, you can perturb by a relevant operator and calculate the leading back reaction in terms of the spectrum at the fixed point. That's straightforward to do. But once the flow becomes strongly coupled, it's a much harder problem.
No, I understand that. I meant for example, like for let's say a short flow or something like that. Can you?
Yeah.
So in those kind of, so for example, you gave the examples of these ON models. So if we consider flows between, so let's say I start giving mass deformations to start break like ON to ON minus 1 or something like that. I mean, just at a perturbative level. So has that been done? Like I can just sweep out like all possible flows in those kind of theories?
I think this has probably been studied at large n in the ON vector models.
Yeah, but so at small n the flow is not as short, but is it short enough for you to kind of apply the technology?
That's a good question. I don't know. I don't know for sure. I'd be surprised if it